Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods, and the learning module on estimation and inference. To understand this learning module, we need to begin with an understanding of the difference between a population and a sample. Let's take a simple example here, one that you might think is silly, but I'm full of silly examples throughout all these recordings. Let's suppose that you want to know what is the average length of the blades of grass in your entire yard, assuming you have a house and you have to cut your lawn. I'm not sure why you would want to know this, but let's just suppose. So what could you do? You could take a ruler and you could go out there and you could measure the length of every blade of grass out there. How many blades of grass are in a yard? I don't know, maybe 1 trillion. That would be the population. But like the reading suggests here in the very beginning of the second section, it says, we take samples because we don't have any idea what the population looks like, or if we do, it's too costly. So how many of us really want to go out into our backyard and lay out there for, I don't know, hundreds of hours to calculate the length of a blade of grass? So what we do is we take a sample. And we might take a sample over there, we might take a sample over here, we might take one in the shade, we might take one in the sun, we might. So we have all these possible samples. What we want to do is we want to use our sampling technique to make an estimate or an inference about the entire population. So here's my advice. When you get to the exam, think of your backyard and you'll be able to answer the question, I'm not going to go and collect data on every firm out there that has paid a dividend in the history of the floor of the New York Stock Exchange. How about if I just take a sample? But what this learning module is going to tell us is that there are some really good ways to sample. There are probably some really bad ways to sample. I mean, think about it. I could go out there and just take my hand and rip out a clump and say, okay, here's my sample. That's probably not going to be an effective and an efficient way to make an estimate about the entire blades of grass. This is cool. I say this to you regularly now here in the beginning of level 1. The Institute has gone to learning modules, and so instead of 427 learning outcome statements for, here, let me go back here, quantitative methods and estimation and inference, now we have just 3. So look at that first one. Boy, there's lots of sample words in there, right? Then we'll talk a little bit about the central limit theorem. Of course, we need to worry about distributions. What did we do in just that last learning module? We talked about the normal distribution and the log normal distribution. Central limit theorem is going to help us make some estimates and inferences. And then we're going to go ahead and try resampling with bootstrapping. We did that in the previous module. All right, so let's start with this first LOS, compare and contrast. So I want you to think about what's going to likely show up on the exam. You'll have a question stem, and there'll be a sentence or two in that question stem that says something like, hey, tell me some similarities, tell me some differences. Do you agree or disagree with a comment made by a financial analyst? So that's what we'll do here on this slide. All right, sampling. Systematic process of selecting a subset or sample from a larger population. All right, so we're going to take that 4x8 section of our front yard as our subset. All right, there's a good proxy for the word sample. There we go. It's time consuming and costly to examine every member of the population. Yeah, that makes perfect sense. All right, so how are we going to do this? We're going to do this assuming that when we select each item inside of the population, if we know it, or the sample, that each one has an equal chance of being selected. Now, this was just a little bit different than my Jordan Spieth example with reaching into the golf club because he only has one driver, right? So he's not going to have 39 drivers in his bag, so you just pick out the one. That's the advantage of all that Monte Carlo simulation stuff we did in the previous recording. And then you can have non-probability sampling. We have a couple of slides here about convenient sampling. Convenient sampling just means that, it's right here. Oh, here, it's on my desk. I'll just go ahead and do that. Suppose instead of just a regular old yard like probably you and I have, maybe we're a farmer and we have a yard that goes 27 miles that way. So what am I going to do? Am I going to go way, way out there and get the sample, what did I say, 4x8 sample 27 miles away. No, I'm probably just going to go right here. And then judgmental sampling, this has everything to do with let's take a step back, look at the global picture and say, all right, the best samples are going to occur over here and over here, but not over there. Judgmental sampling. When I ever hear that word convenience, I always think of that great line in the Stephen Wright comedy. Have you guys ever listened to Stephen Wright? Please, there's your homework assignment. He went to an inconvenience store and he asked the salesperson to help him get it, and the guy said, "Get it yourself." An inconvenience store. I hope I got some of you to chuckle on that one. All right, compare and contrast. All right, so let's do simple random sampling versus stratified sampling. So just think about what those words mean. Simple random sampling, what does that mean? That means that, and I'm guessing that you guys know Excel fairly well, and there's a random number generating function in there. So you just hit that thing, imagine you have a row of 1,000,000 numbers, you hit that thing and it'll just randomly pick one of those things. So it has an equal probability of being picked. There's the simple random sampling. But what happens if we want to compare the difference between the lengths of our blades of grass in the sunshine versus in the shade? So there are differences within the population, right? So we might need to divide them into their component parts. So how about if we do this and we divide them into stratums, and we have all of these stratas: shade, sun, lots of water, no water. And we can do this with a population of stock returns: dividend paying firms, non-dividend paying firms, firms that have leverage, firms that have no leverage. And there are tons and tons of ways that you can do this, and you don't have to do it. In my two examples, there were just two stratums, but you could have a continuation of stratums, like hey, firms that have no leverage and then low leverage, and you'd have to identify low leverage, like a debt equity ratio, some small number, and then moderate leverage, and then intermediate leverage, and then you can do this however you want. So think about this: the stratified sampling model is going to work if you know that the population doesn't look exactly like each other for whatever reason. So then, imagine breaking this into a bunch of different strata, and then you just take a random observation out of each one, and then you go ahead and combine all that stuff, and then you can do your regular, kind of calculating means and standard deviations. Let's take a look at just a quick example. Suppose that we have a sample of 1,000 stocks. Well, do those 1,000 stocks, do they all look exactly like each other? And of course, they're going to have some differences. What did I say earlier? Dividends and leverage. But suppose we just divide them by size: small caps, mid cap, and large cap. And so here's our population of 1,000 stocks. And how are we going to divide this into strata? Well, suppose we collect 40, and it's 40. There's our sample size. So we'll do 12. There's just simple math there. And so we can do the same thing with the mid cap and the large cap. So we have 3 of these stratas, right? Now we're going to have really good conversations in levels 1, 2, and 3 about this gigantic concept of artificial intelligence and machine learning, and we're going to go ahead and talk about clustering. Here in level 1, we just have a super simple idea of saying something like, maybe when we pull things out of the population or our sample, that there will be clusters. So look at the picture there. That makes perfect sense. There's a cluster. So you can group one over here and then group another one over here. And you can do this in one stage, or you can do this in 2 stages. I mean, if you're smart enough to program an algorithm, you could do it in, 29 stages if you want to. That sounds a little bit like overkill. But when you have this extra step in there, that's called 2-stage clustering. All right, let's get back to those non-probability sampling methods. I said this to you just a moment ago. Here we go. Convenient sampling, accessibility, and proximity to the researcher. This is what I was saying earlier. 27 miles away. There's no way I'm going all the way over there. Judgmental sampling, researcher's knowledge, and professional judgment. I mean, those two are fairly obvious definitions. All right, so what did I say to you in the very beginning of this slide? We needed to know the difference between the population and the sample, which means that we need to ask our question about the distribution of the population and the distribution of the sample. So suppose we have this population, like all the blades of grass in my yard, and we go out and take a sample. Well, suppose that the sample is super different than what the entire population is. Now, of course, we might not know what that population is going to be, but we can suspect. We have our suspicions, we have our ideas. So I'm going to go ahead and read this to you, and then I'm going to tell you what it means. You ready? Given a population described by any probability distribution having a mean of mu and a finite variance of sigma squared. All right, so what does that mean? That means that we have this population, like my grass in my yard. It has a population mean. You know, what is the average length of grass? You know, maybe it's 4 inches, whatever it is, and a finite variance. Maybe if I take the square root of that, the standard deviation might be a half an inch or 2 inches, whatever it might be. All right, so then what happens? If we take a sample of that, wherever the sample is, over here or over here, wherever that sample is, and we do this randomly, then the sample ought to be nearly normal, with an expectation that the mean is going to be the same as the population mean, and the variance is going to be the same as the sample variance is going to be the same as the population mean. Now, look at the very end then it says, when the sample size n is large. So we have to ask ourselves the question, what in the world is a large sample size? So think about it. I go out and I get 7 blades of grass. Is that large enough? Probably not. Is 100 blades of grass large enough? I don't know. 100 out of a trillion blades? Probably. So here's the standard. N is sufficiently large. That's one of those terms that sounds like a lawyer came up with it, but it's really a statistician. Sufficiently large. I remember my econometrics professor in graduate school telling us, you know what? Everybody thinks that if the sample size is over 30, that you can go ahead and make some reasonable conclusions. And he said something like, you know what, I tend to agree with that. But however, it's not etched in stone. But I'm guessing that the Institute wants you to remember that number 30. And by the way, we're going to do some confidence intervals and other kinds of tests throughout levels 1, 2, and 3, where we're going to be required to take a look at n. So that's going to be important. Just remember, sufficiently large, n equals 30. Now, I want to make sure I emphasize this point here. So look at the very first sentence up here. I'm not sure I emphasized this earlier. Given a population described by any population distribution, any probability distribution. What that means is that my blades of grass in my population, they could follow any probability distribution. But when you sample them, it's going to turn out to be almost a normal distribution. That's important. All right, so what do? We take the sample and then we calculate the mean length of the blade of grass. What did I say it was earlier? 4 inches. Well, then we need to ask ourselves the question, and this goes back to the title of this learning module of Inference. We have to ask ourselves the question, okay, if the average length of a blade of grass in my yard is 4 inches, how wrong could I be if I randomly walk to my backyard and pick a blade of grass? Maybe that blade of grass is 2 inches, in which case I'd be really wrong, right? I'd be way off. Maybe it's 8 inches. I'd still be way off. Maybe it's 4 inches. So we need a way to measure the degree of error. Sometimes in front of my students, I'll call it the degree of wrongness, because I use that because wrongness is not a word, but I always talk like that so the students can remember stuff. So let me read that first teardrop point to you. Standard error of the sample mean refers to the standard deviation of the distribution of the sample mean. So we take a mean over there and a mean over there from all these different samples, and that standard error is the standard deviation of all of those sample means. So what that central limit theorem implies is that there's our sample variance. It's equal to the population variance in the numerator and then divided by the sample size. So let me just quickly remind you, to get the square root, to get the standard deviation, you just take the square root. So there we go. Look at the green box. This is a likely question that's going to show up somewhere in level 1, level 2, to compute the standard error of the sample mean. So just take that sample standard deviation and divide by the square root of n. Now the variance then, the sample standard deviation, is the square root of the variance. So look in the purple there. Notice what we're doing. We're taking each of those samples, right, and we're subtracting the mean. So x sub I minus x bar. There's the sigma. So we're adding all those. We're squaring it. This is the third time I think I'm going to remind you about that little lesson I give my students. We square it just to get rid of the negative. Remember, I walk in front of the class and I play that little game. I won't go through that again because this would be the third time that you've heard it. So here we go. Here's my advice. Make sure you watch these things in order so that you can catch up to all my little silly examples. All right, so look at those 3 teardrop points at the bottom of this slide, and they probably have some good potential exam questions. All right, so what are we doing? Standard error of the sample mean gives us an estimate of the variability. So this is what I was saying earlier about the degree of wrongness, the degree of error. You know, suppose there is a standard error of 0. What does that mean? That means that you're going to be right all the time, right? No matter where you go, you're going to reach down into your lawn and you're going to pick out a blade of grass and it's going to be 4 inches, right? So x sub I minus x bar, 4 minus 4 is 0. So no matter how many times you do that and square it and divide by n minus 1, you're still going to get 0. So it gives an estimate of variability. And this is going to be super instructive for us as we move through the program, because we're going to use standard deviation and some other measures of degrees of wrongness as estimates of volatility. Oh my gosh, volatility is going to be so important, especially when we get to the Black-Scholes-Merton option pricing model, but that's a conversation for another day. So look at the bottom teardrop point. A lower value of the standard error indicates a more precise estimation. So let me repeat this. I said this in 2 of our previous learning modules. You ready? So standard deviation, in this case we're calling it a standard error, gives us a measure of our degree of error, which means if you have low standard deviations, you have, well, let me just read this, a more precise estimation of the population mean, which is very likely to be kind of the verbiage that the Institute uses on the exam. Why is the standard error so important? Okay, so haven't I been just describing this here? Yeah, larger value, less precise. Yeah, intuitive from its formula. All right, so this makes perfect sense, this slide here. So let's take a look at an example. Workers have a mean hourly wage of 12. Population standard deviation of 3. What's the standard error of the sample mean? Well, let's just take 3, standard deviation of 3, divide by the square root of 30, and there's 55 cents. So the mean wage is 12, and here, let me put it this way, our degree of error is 55 cents. So when we go and we look at this next worker, will this next worker have a mean hourly wage? Will they have an hourly wage exactly of $12? Well, they might, but we know that there's going to be some variability. So 55 cents above the 12, 55 cents below the 12. Oh my gosh, we're going to talk about normal distributions. We're going to talk about central limit theorem. I'll go ahead and give you a sense that, remember, 68% and 95%. Can you put those 2 percentages in the back of your brain? I'm going to call on you at some point to memorize those and to give me those 2 percentages. All right, those of you who watched, and I hope that's every single one of you, the previous recording, we talked at length about Monte Carlo simulation and bootstrapping. Well, this is exactly what we've talked about before. That was the Jordan Spieth example of reaching into his bag, repeatedly drawing samples from the original observed data. Yeah, so what are we going to do? We're going to reach into the bag and pull something out. Now, in my previous example with Jordan Spieth with all the golf clubs, let's go ahead and look at it through my current lawn example. So what are we going to do? We're going to simply just go out to our yard and pull out a piece of grass. Maybe we're going to pull out 100 pieces of grass, maybe 1,000 pieces, whatever it is, and then we're going to run some tests, means and standard deviations on there. And then we're going to do it over and over and over again. So think about, this bootstrapping. It, of course, natural conclusion is Monte Carlo simulation. You do this hundreds of thousands of times. Now, there's the standard error of the sample mean with bootstrapping. So notice in the denominator there, we're dividing by not the square. Here, let me go back here. What did we do? The square root of n, but with bootstrapping, we're going to divide by the square root of n minus 1, with sampling, but we're not going to call it n, we're going to call it b. Look at b, number of resamples drawn from the original sample. And then notice the thetas over there, that's still the same thing. We're going to take each one, right, and subtract the mean and then square it for the rest of those things. Now look down at the very bottom diamond point. Resampling can be applied to estimate confidence intervals. We'll do confidence intervals some other day. Let's take a quick example here. We have price earnings ratio, 100 distinct stocks over a given period. You draw a sample of 1,000, obtaining 1,000 PE ratios. All right, so you do this over and over again. The mean across all resampled stocks, 5/8. Some of the squares, 2.3. All right, so this is what the Institute likes to do. So we do as well. We give you these sum of the squares. So that's just the sigma. And then the parentheses and squared, that's 2.3. So what is the standard error of the sample mean closest to? Well, you can do the math right there and you get 0.05. Let's go ahead and end on jackknifing. What did I tell you earlier? This is where we repeatedly draw samples from the original observed data. So we do this with, we can do this with replacement or without replacement. So this is what I was saying earlier, right? Look at that last arrow point. Used to reduce the bias of an estimator and to estimate the standard error and the confidence interval of an estimator. So just remember what I was saying earlier, that jackknife, you kind of take one out and then run some statistics on the remaining sample, and then you put it back in and you take out another one and you do the same thing and you do it and you do it. And so those are probably going to result in pretty similar distributions, right? All right, so here we go. We've finished all 3 of these learning outcomes. So there are 5 questions at the end of this learning module. I think I'm going to go ahead and give you credit. Go ahead and take 5 minutes right now. You ought to be able to do these pretty quickly. We've covered them all. So hey, thanks for watching and have a great day and good luck studying.